Probably I will be the first one to start. So my first question is regarding this size convergence that you have shown in this plot, where you actually above 2 by 2 unit cells you are converging. And I was wondering how you do this kind of plots. So this is numerical computations, and then you make the evaluation on.
Right. So it is.
Yes, this one.
Yeah, exactly. So it is just a numerical computation. We apply this these macrokinematic variables with periodicity conditions for the fluctuation, and then we solve this this unit cell boundary value problem, and then we plot this moduli versus the number of unit cells. Huh?
But you said you have a periodic boundary conditions, right?
Right. Yes, we have periodic boundary conditions. Yeah.
Okay.
Yeah.
Okay. Just curious, because I mean, when we did some size effect, we were rather leaving free boundary conditions, like free traction boundary conditions, and just studying. But here you are saying that you have this periodicity on all the cases, and then you apply the homogenization on them.
Yes, exactly. So there is another size effect, the one that you mentioned, in which we have free boundary conditions. So for instance, we make the bending of a beam architected with some unit cells, like hexagonal unit cells. If we don't have enough unit cells on some edge, then there will be some typical edge effects. Huh? So because we do not have enough unit cells to make homogenization, huh? But this is another mechanism actually.
Okay, I missed that point. Okay, thanks. Then I have another question regarding actually the same kind of behavior. So here you, when you apply this homogenization, you look at getting the effective property for some static-like tests. So compression, shear, and this kind of bending.
Right.
And do you apply the same homogenization, or have you tried to apply it to compare the dynamic effects, and especially the, like, let's say, if you take a dispersion relation, higher bands for the microstructure, and eventually the higher bands for the micromorphic continua?
I'm not sure if I caught your question correctly. You were speaking of dynamical effects. But here we do just statics, huh? Okay. Dynamics is another work, huh?
Okay. No, I was maybe just wondering if you tried. No.
Yeah. We did. It's true. We did some work on dynamics, and so what we did in 1D. So, for instance, for stratified media, is to incorporate or to compute the effect of micro inertia. So we incorporated micro inertia and combined it with a strain gradient formulation, for instance, and we show that there is some effect, of course, some difference if we don't, or if we do incorporate micro inertia effects. So it has an impact. For sure, it has an impact on the dynamics.
I mean, let's say differently. The reason why I'm asking the question is that, for example, when you take this micropolar continua or Coursera continua, you have some of the variables that are very important in the dynamic regime. They are much less important, let's say, in the static regime. However, if you want to recover all these parameters in the static case using static tests, then you have to impose some boundary conditions that are rather weird. I mean, like for example, if you look at the work of Roderick Lakes, he was taking some of the bar, he was twisting them, but still having some weird boundary conditions, which is fine on, let's say, today with the finite element, it's fine to implement such boundaries, but it's rather difficult to make it in any experiment. And sometimes the easiest way of, let's say, measuring this kind of effects is rather to do some dynamic tests, and to get from the dispersion relation to get some of the parameters. But
okay, yes, this is a way to access. Right. Okay. So people do it the other way around. They move from static to dynamical properties, or if you use Christoffel equations, you can access static properties from wave propagation features. Yes, exactly. Yeah.
Okay.
Yeah. So we have done some work, and you may be aware. I don't want to make too much advertising of myself, but we have done some work on Willis elasticity. So we have published recently a paper in which we compute actually all these non-local behaviors for composite materials.
Okay, I missed that paper, but you could send it to us, or we could upload.
Yeah,
upload
sure. I can. Yeah, right.
Any other question from the audience?
Yeah, sorry, it's Marcus Wheel from Strathclyde University. Thank you, Jean-François, for a really interesting talk. Could I ask a detailed technical question about the slide that's in front of us at the moment? In there, you have the green circles. Are they inclusions, as in more rigid than the surrounding matrix, or are they voids, as in more compliant than the surrounding matrix? Would it make any difference if you changed from inclusions from stiffer inclusions to more compliant inclusions or voids?
Right. I think we have considered the case in which these inclusions are more rigid than the surrounding matrix. I know some people doing the converse to have some resonance effects in these inclusions, which are then soft, or sometimes there is a coating, right, with a soft elastomer around these inclusions. But here I think we have, I didn't include actually a table with properties. Okay, but this was just to illustrate, but yeah, those are more rigid by a factor 10 or 100 compared to the surrounding matrix. Yeah.
Right, but homogenizing within the context of the micromorphic continuum obviously works here. There's a paper, isn't there, by Bigoni, where he considers this case, but analytically does the homogenization in terms of the Cauchy continuum, and he shows it doesn't work there, I think.
Yeah, so here we need a high enough contrast, otherwise this effect will not appear, or we will be very weak.
One other point I noticed in your slide, where you reclassify, if you like, the family of higher order theories. Presumably at the bottom, although you've not included it, is classical Cauchy elasticity. It will degenerate to that.
Cauchy will be, I didn't show it because maybe it's too common.
Yeah, trivial,
Cauchy will be really at the very bottom. But of course, it will be reached in the last step.
Yeah. Thank you.
Thank you. Any other question? Sebastian?
Yeah, thank you for this very interesting talk. Okay, in fact, so I guess that you use some asymptotic expansions to get there.
Not exactly. It's not asymptotic expansion method. We get a polynomial expression of the displacement, but which is not an asymptotic. It is exact. In fact, it is asymptotically exact as a result of the theory we have developed. So there are no. Of course, we can say that the remaining part of the series is hidden in the displacement fluctuation. But considering only the homogeneous part, it describes exactly the micromorphic continuum.
But you've got corrector type results still.
In the sense that we have higher order powers of epsilon. Yes, of course. Yeah, sure.
So, okay, but epsilon, so I find, okay, so I mean, I get my usual annex problem. So with periodic conditions, then I solve this annex problem.
Yes.
And in some kind of, I mean, and you have a hierarchy of annex problems, no? I mean, because
yes, of course, there are several annex problems, yes.
And each annex problem fits the forcing term of the next annex problem.
Yeah, no? they are recursively coupled, exactly. Yeah.
Okay.
Yeah.
I mean, this is very interesting. I will have to read your papers, but so you say that we are, with your approach, you can generate all kinds of generalized continua. So
well, not all kinds, because there may be some, all known ones, because it could be some microstructure which requires some, I don't know, some new effective medium. Huh?
But this is all static. Huh? These are static effects.
These are static, yes, only static.
And so, okay, and of course, you had higher and higher order corrections, so higher and higher order tensors.
Right.
But when it's not centrosymmetric, these are the even or odd rank tensors that contribute.
Of course, if it is centrosymmetric, we have some vanishing coupling terms.
Okay.
It is non-centrosymmetric. This is the most interesting situation in application, because then we can trigger all terms. Huh?
Yeah. And so when it's non-centrosymmetric, which are is it the even or the odd rank tensors?
It is the odd order tensors that will be activated. Huh?
Yeah. So,
for sure.
So 3, 5. Yeah.
Mm-hmm.
Okay. And so you said that you also did Willis. You mentioned you also did the Willis.
So we computed. What we did is to compare the prediction of Willis elasticity, but in dynamics, to compute dispersion diagrams. So optical branches based on Willis elasticity. Then we compared with, let me remember, we compare with local in time but non-local in space theories, and we compare with strain gradient theory, and then we compared with block theorem, which gives the exact solution. And we show that Willis theory improves actually quite much compared to other theories, and it fits relatively good to the reference solution when we use block theorem. Okay. So there is a theory. It was actually a little bit challenging to derive this, because we have extended ill macrohomogeneity condition, but to the dynamical regime, using the Floquet-Bloch decomposition of waves. But then it makes it very easy to obtain the dispersion relation, because everything is in full Fourier space. So naturally you get the dispersion relation, and then all the job is done in some sense.
And so this was published recently?
This is in European Journal of Mechanics.
And this is very interesting.
I'm curious to see this the comparison, especially for the higher bands.
Yeah.
Because I'm not aware that this was really done by anyone else before.
There was some, the work of Qishang-E and Nassar. Huh?
Okay. You said Nassar, yes.
And Nassar, and this was...
And Offray.
Yes. Nicolas Offray. Yeah. Mm-hmm. But for me, the physical basis of this phenomena is still challenging to understand.
Yeah. Mm. Okay, thank you so much. It's I mean, I did not know your work, so I'm very happy that I get to know it, and I can now start reading your papers. Thanks.
Thank you, Sébastien. Do we have some more questions? Just looking at the others, apparently not. Let me ask you a last question, Jean-François, regarding this very advanced mechanical aspect. Is this commonly used to try to connect the, let's say, the atomistical mechanics to the continua, or is this probably one of the best way to account the size effect and the boundary effect?
You mean atomistic simulations?
Yes.
Yeah. We are starting to work in this direction. Of course, for me it's pretty new. Probably this is one. This could be the right way to proceed. Huh? But then we face the problem of statistical disorder, because as we move to the lower scales, to these atomic scales, that means the atomic configurations may be very disordered unless we consider some model materials like crystals, in which we can still use some assumption of relatively local order, yes, local order periodicity. Yeah,
but still, for very good crystals, this should work, and this should be applicable. I agree that even if you face some dislocation or anything that breaks, let's say, that brings more inhomogeneity inside, then it would be hard.
Yes, exactly. Especially interfaces in polymers, but also in other materials are very challenging, because this is a place where we expect to have strong gradient of properties and deformation and the microfields. So this is probably where for these interfaces we should use this combined molecular dynamic simulation with some kind of homogenization theories.
Yes. Yeah. Okay, thank you. Is there any other? Yeah, Sebastian?
I have one last question. So in terms of the mathematical framework, I mean, the functional framework, I mean, so you proceed with your method and then you prove the convergence result. I mean, how do you, so do you have any specific tool to, show the convergence, or it's just?
You mean asymptotic convergence, for instance, for?
Well, with respect to your parameter epsilon, I guess that when you add more and more terms, you get a better and better corrector result. So your corrector result, you have epsilon to the power n. Some, I
know, of course, in the framework of, but here I would say that. So we get them as it is written on this slide, for instance. Huh?
Yeah.
What is more important is to look in a numerical manner, not only in a formal mathematical way at this convergence, but to look at apparent properties, because this is an ideal framework of periodic materials. But if we take a macrostructure, it will not have infinite number of unit cells. So it is also very important for me to look at apparent properties and how these apparent properties will vary or will converge with the microstructure. Yes. So it's not so mathematically oriented, but it's I would say a mix of numerical sensitivity analysis and also using these enriched theories to compensate for the fact that we may face situations in which we don't have enough elements of unit cells.
Also, so obviously you have this finite size effect. So your body has a, so you have so is it encompassed already in your theories? The finite size effect. I mean, somehow it is, no?
No, it is not included here, because here I focused on micro to meso response.
So okay, so you don't have any boundary layer type effect encompassed in any of the.
No, not really. This would appear if I would. Well, actually, it could.
But then I'm a bit because in your numerical examples, you have shown some finite size bodies, no?
Yeah, here. So here exactly. So this is the exception where it will appear. So we didn't study that. Huh?
So this might explain the little discrepancy then.
Yes, because so we should probably increase the number of unit cells and see if we improve actually the predictions, because we expect, of course, some edge effect. Huh? But this edge effect is responsible for these small differences here. Yeah.
But I'm a bit, again, I'm a bit confused because I thought that these kinds of also of you know, effect I mean the typical size. You have two scales anyway in your problem. You have two scales. You have the micro scale and you have a second scale.
Mm-hmm.
So what? So you have the cell. So you have the cell, and then what is the other? What is the other scale?
The macro, for instance, this length, the macro linear size.
But assuming that it's a supercell, this is what you assume. So it's like on a torus, there is no boundary. This is what you assume.
Not exactly, because we solve the macroscopic boundary value problem.
But what do you impose as conditions on the?
So here, yeah, we need, of course, higher order boundary conditions like absence of rotation. So it's fully bound in terms. So we need also this higher order condition on the micro deformation.
Yeah.
Of course, because we get a fourth order differential equation in space. For this one, so we need four types of boundary conditions.
So here it's the Kirchhoff law or the mean plate equation. Which one is it?
No, it's not. It's not a plane which is bent out of its plane. It's a plate which deforms inside its plane still. So we are not using a plate model for this.
So it's 3D, in fact.
It's 3D, yes, exactly. Yes, of course,
3D.
it has a thickness. Yeah, it has a thickness. So we solve it with free form as a macroscopic. So in fact, we are solving this macroscopic boundary value problem here with homogenized moduli. So it's a full 3D formulation at the macro level, in fact.
But why do you end up with fourth order? You have some kind of Bilaplacian?
I don't remember exactly, but yes, because K will be the gradient of chi, and because of this specific form of the homogeneous displacement, if I remember correctly, we have two kinematic variables. We have the macro displacement and we have chi. Yes.
Okay.
And so we have two coupled equations here that we have to solve for this kinematic degrees of freedom. So if I remember correctly, we get the classical, this one is a kind of classical differential equation, PDE, and the second one is a non-classical one because we have chi and the gradient of chi. Yeah. So I'm not sure, I don't remember exactly what is the differential order of this.
So when you have 3 dots, it's a triple contraction. I mean, this kind.
Yes, exactly.
Okay.
Here it's triple contraction, it's double contraction. Yeah.
Okay. Yeah. Just to. Whew. I mean, I think we need to sit down and read your papers because
have good eyes. We need to have good eyes, not to miss any dot. Huh?
No, it's not this because it's just, without reading the papers, you can only guess things and no,
yes, sure.
It's a fantastic introduction I don't know your theory, so I cannot say that I understand anything yet, but I think I understand the philosophy. I think I understand what is the spirit of your approach, and I like.
At the end, the philosophy is more important than the technique. Huh?
At the end, if you don't like the philosophy, you don't want to digest the technique. So first, you need to like the philosophy.
99% transpiration and technique, and then we make this 1% philosophy as a big part of the cake. But this is maybe an illusion.
Okay. Okay, so thank you again, Jean-François. It's great.
You're welcome. Huh?
Yeah, great.
So thanks. Thank you very much for the overall for the talk. So everything was recorded, and as I said, it will be made available in the coming hours, if not days. And of course, if anyone is willing to cite the talk of Jean-François, he's welcome, and the DOE will be attached to the talk and available on the website. So thank you very much. And,
thank you again for the organization of this webinar. Huh?
Thanks.
I wish to follow the next one of the series. Huh?
You're welcome. The next one will be given by Herald de Giesen, and it's more on plasmonics in optics on the 12th July.
Okay, very good.
Okay, thank you very much, and goodbye.
Goodbye, everybody. Have a good day.
Thank you all.
Thank you.
Bye-bye.
Bye.